from galaxies. He observes that the farther the galaxy, the longer the wavelength of light it emits. Light pitch. That's a decimal point, 42 zeros, and then a 1. It's an unimaginably small amount of time. Yet in this first tiny beat of Planck time, something happens that shapes the next 13.7 billion years. Out of the fireball, the 4 fundamental forces of nature form. Those forces underpin everything around us. Gravity is the reason stars and planets form. It rules the moon and tides and keeps us on the ground. Electromagnetism lights our cities, connects our phones, and runs our computers. And the 2 nuclear forces, strong and weak, bind the particles that make up our bodies and power the furnace of our sun. We're here because in the first second after the Big Bang, the 4 forces are created. Without them, the universe would be a featureless fog of radiation.
If there were no forces, nothing would happen. There'd be no television. There'd be no sports. There'd be no love, no hate, no human tragedy. All the things that make life worth living.
But in the first beat of Planck time, the 4 forces are still rolled into a single superforce. Gravity, nuclear, and electromagnetic forces have not yet divided. Physicist Michio Kaku studies how the forces split apart.
I like to think of it as a crystal. A beautiful, symmetrical crystal, all the forces unified in their elegant simplicity at the beginning of time.
As our cosmic clock takes one more tick of Planck time, the tiny fireball universe expands. The 4 forces start to break apart. It's like rapidly cooling a super hot crystal. Cracks form.
It began to shatter into 4 pieces. The first piece to break off was gravity. Then the nuclear forces began to split off. And finally, we have this fragmented jewel of what used to be the superforce.
Those 4 fragments are still at work. Gravity keeps Earth in orbit. Nuclear forces make sunshine. And electromagnetic radiation, the light that bathes our planet. We're just fractions of a second into our journey, and already the foundations of our world are forming. The fireball universe. Still smaller than an atom, and 1,000 trillion degrees. To discover how the universe expands, scientists use telescopes so powerful they can see the past. When astrophysicist David Spergel looks up, he sees history.
As we look out in space, we look back in time. Light travels at a finite speed. So the light we see from the sun takes about 8 minutes to get here. We see the sun not as it is, but as it was 8 minutes ago. We look out at the night sky, we see the nearby stars. They might be 10 or 20 light years away. We see them as they were 10 or 20 years ago.
The Big Bang was so powerful and so hot, remnants of that heat still survive. The heat began as super hot X-ray radiation. As it stretched and cooled, it became visible light, shifting from blue to red, then becoming microwaves, and finally radio waves. This faint radiation shines down on Earth all the time. It's called cosmic microwave background radiation, or CMB.
The cosmic microwave background is the echo of creation itself. It's the embers, the afterglow of the original shock wave that created the universe. If we had microwave eyes that could see microwave radiation, then every night we would see the Big Bang coming out. Looking at the heavens, we would actually see an explosion.
More than 13 billion years later, we have a way to see this cosmic glow with the naked eye.
You take your TV set, switch it between channels. A couple percent of the static that you see on your TV screen is radiation from the Big Bang.
This cosmic radiation is a direct connection to the Big Bang. It also reveals the universe entered a new phase, less than a trillionth of a second after its creation. Cosmic radiation is the key to discovering what happens next.
I think that's an interesting thing.
This